Hi, welcome to Sherwin-Williams. What can I do for you?
Pete,
Noah, hi there. What's going on?
what are you doing behind the counter?
Me? Oh, I work here.
But I thought you were a software engineer.
Oh, I am. And, as you might remember from our ad infinitum episode, I also work at Hilbert's Hotel.
How can you work at all these different places?
Well, as someone who works at a hotel with infinitely many rooms, I do know how to get a lot of stuff done. Anyway, what brings you in?
I need some paint. I just got this really cool horn, and I want to paint the outside of it a different color.
Okay, so how big is it?
Pretty big. Hang on a sec. I've got it on the truck outside. Let me back it in. Hang on. Okay, I can't exactly back it in. The narrow end of the horn hangs way off the back of the truck. Let me turn around and just pull in straight. There we go. So what do you think, Pete? How much paint do I need?
Whoa.
What's the matter?
Do you know what kind of horn that is? A really cool one. It looks like a really long vuvuzela.
You know, those colorful plastic horns that soccer fans love to blow during games?
What you've got there is a Gabriel's horn. It's a geometric object that has infinite surface area. I'm sorry, Noah, we just don't have enough paint.
What? You don't?
I'm afraid not. Remember last summer when I tried to paint all the prime-numbered rooms at the hotel? That didn't exactly work out, and not because I used millennial paint either.
Hang on. This can't be right. I was just cleaning the horn at home, and I filled it with water, so it obviously isn't infinitely large on the inside.
Yeah, that sounds about right. But I didn't say it has infinite volume, just infinite surface area.
Wait, so it has an infinite surface area and a finite volume?
Yep. This baby's pretty sweet.
How is that even possible?
Tell you what, my shift here is just ending. Why don't we head over to the math club and we can talk all about surfaces of revolution.
All right, Pete, so what is Gabriel's horn?
Well, like you said, it looks like a vuvuzela, but it's infinitely long. One end flares out like the bell of a trumpet, and the other end tapers off to infinity, getting thinner and thinner as it goes. Technically, it's a kind of mathematical surface called a surface of revolution, which probably just raises another question.
Yeah, what's the surface of revolution? And don't go answering me with some other term that I'm going to have to ask you about.
Okay. A surface of revolution is a particular type of geometric object that is generated by taking a geometric figure, like a circle or a curve, and revolving it about a fixed axis. As the figure revolves, it traces out a surface in space.
Is the axis just a straight line, or what should we be picturing here?
Yeah, it's a line. The basic picture here is this. You've got some shape in the XY plane, and you draw a line wherever you'd like. Then you imagine revolving the shape around the line, so the shape kind of lifts out of the plane and moves through space.
Oh, okay, I see. What's a simple example we can start with to help get a mental image of how this works?
Well, let's start with a circle, and let's imagine that the axis passes directly through the center of the circle. So the axis will align with a diameter, and it intersects the circle at a pair of opposite points.
So the axis would divide the circle in half.
Right, it would.
So does this mean we could spin the circle on the axis? And if it spins really fast, it would look like it's kind of making a sphere?
Oh, yeah, that's a cool way to imagine it. And in fact, a sphere is exactly what we would get. As the circle revolves around the axis, its points trace out a sphere.
You know what this is kind of reminding me of is when I used to do woodworking and I would stick a rectangular block of wood on a lathe. Once the lathe was up to speed, as it spun faster and faster, that rectangular block would really start to look like a round cylinder. So if we started with a rectangle and made a surface of revolution by rotating it around a center axis, would we get a cylinder?
Yeah, we would. And, I really like the lathe metaphor that you just introduced. So let's imagine a block of wood spinning on a lathe. And if we shape it using a chisel, we'll end up with a curvy shape, and that shape will have rotational symmetry along its central axis, right? It's been spinning. If you now use a pencil to trace the curvy edge on a piece of paper, you'd end up with something like the graph of a function.
That sounds kind of like creating a surface of revolution in reverse. We started with a 3D shape, and by tracing the edge, we created the graph of a function that could be used to make that surface of revolution.
Yeah, that's exactly it. In fact, that function, the one that you would draw, it is the one and only function whose surface of revolution is the exact shape that we pulled off the lathe. Now, Gabriel's horn is the surface of revolution that we get when we revolve the graph of the function y equals 1 over x about the x-axis. And we add an additional constraint, which is that we only look at values of x that are greater than or equal to 1.
And that really makes sense because y equals 1 over x is defining part of a hyperbola that is asymptotically approaching the x-axis, never quite getting there. So of course, when we revolve it to make a 3D shape, we're going to get the same sort of effect. Essentially, the narrow end of the horn extends forever and gets skinnier and skinnier like a tube that never closes up all the way.
Yeah, and here's some interesting history. Gabriel's horn was discovered by a mathematician, an Italian named Evangelista Torricelli, who was in fact studying revolutions of hyperbolas about their asymptotes. And he caused quite a kerfuffle when he published his results, namely that although Gabriel's horn is infinitely long, it only contains a finite volume. And I think the rest of the world was shocked with disbelief.
No way. Yes way.
Hang on. So if Torricelli was the one who did all the work and found out this cool fact about the volume, why do we call it Gabriel's horn? Why don't we call it Torricelli's horn?
Well, it is also called Torricelli's trumpet, so it does pick up his name at least sometimes. I don't quite know why it's called Gabriel's horn, but I do know that it was named after the archangel Gabriel, who in biblical stories would blow a medieval-looking horn to announce special messages from heaven.
Okay, but just to be clear what we're talking about here, Gabriel's horn is purely an abstract mathematical concept. It couldn't exist in real life because nothing in real life can have an infinite surface area.
Right. Now, at the time that Torricelli announced his discovery, which was back in 1641, many philosophers were sort of thrown for a loop because they were questioning whether or not the universe could actually hold an infinite object. And as far as we know today, it can't. But a couple of hundred years after Torricelli's discovery, I think it was in 2010, Hyundai, the car company, built a really big vuvuzela down in Cape Town in South Africa. And I believe it's 35 meters long. So, pretty close to infinite.
I don't think I'd be able to back that vuvuzela into the paint store on the back of a truck either.
I'm glad you brought us back to the paint store because there's an interesting kind of paradox here, and it's related to the question of whether or not we could actually paint the horn. As it turns out, Gabriel's horn has infinite surface area, meaning that all the paint in the world wouldn't be enough to paint the horn's surface. But as we've already said, the volume of the horn is finite. So we could actually fill it up with paint. But if we did that, wouldn't it mean that every point on the inside surface is touching paint? So What's going on?
And doesn't that actually mean that if the horn itself were made of glass, you could make it look like you painted it just by filling the inside, but there'd be no way to actually paint it?
Yeah, I think that's right. It feels like we kind of painted ourselves into a very curvy corner.
Okay, so let's get to the heart of this apparent paradox. First, why isn't the volume infinite? If the horn itself is infinite, isn't there always more space to be filled?
There is always more space to be filled, but that doesn't mean the volume is infinite. And to understand this, I think we need to talk about infinite sums. We need to understand how to add up an infinite set of numbers. So let's dive in and start with an example. How about this? What do you think we get if we take 1 plus a half plus a fourth plus an eighth and so on? Do you think we can figure out what this might equal? Sure. Since we can only add two numbers at a time, let's not try to add everything up at once. Instead, let's start small. So the first two terms of the series are 1 and a half. If we add them together, we get 1.5. We do. And we call that the second partial sum because we added the first two terms in the series. And now if we add 1/4 to that, what do we get?
Well, 1.5 plus another 1/4 is 1 3/4. Hey, I'm pretty good at this.
Settle down, Torricelli. We've only got the third partial sum so far. It's the sum of the first three terms, right? 1 plus a half plus a quarter equals 1 3/4.
Okay, so to get the fourth partial sum, we would have to add 1 3/4, which is the third partial sum, and 1/8, which is the fourth term in the series. So the fourth partial sum would be 1 7/8.
Yep. And I'll do one more for good measure. The fifth partial sum is 1 7/8 plus 1/16, which is 1 15/16.
All right, so if I've got this right, the first five partial sums are 1, 1.5, 1 3/4, 1 7/8, and 1 15/16.
You got it. Now, here's the question. Do you see a pattern there?
Well, the sums are getting bigger, and they seem to be getting closer and closer to 2. Each time we add another term, we get a mixed number that's between 1 and 2, and the fractional part of each mixed number, 1/2, 3/4, 7/8, 15/16, the numerator is always one less than the denominator.
Right. And those denominators happen to be powers of 2. So let me give you the next few partial sums. 1 31 32nds, 1 63 64ths, and so on.
You know, it sounds like the partial sums never make it to 2, though, do they? Kind of like an asymptote approaching its limit.
Yeah, you're right. They never make it to 2, but they get arbitrarily close. Really, really close.
This sounds an awful lot like Zeno's paradox. We're adding a bunch of numbers together and they seem to be going somewhere, but in the end, they don't really get you anywhere. Isn't that a problem?
Well, actually, this is the very sequence that people use to disprove Zeno's paradox. The partial sums themselves, you're right, they don't ever equal 2, but as an infinite sequence, those partial sums converge to 2. They get as close as you'd like them to get. And in fact, this is how mathematicians define infinite sum, as a convergent sequence of partial sums.
You know, I don't want to toot Gabriel's horn here, but I think I'm starting to get what you're saying.
Okay, well, let's get back to Gabriel's horn then.
Okay, you were going to tell us how to see that the volume is finite.
Oh, right. Well, I think the next thing to do is to talk about Gabriel's cucumber.
Gabriel's cucumber? What is that?
Well, it's actually just a metaphor that I made up. So imagine that we have revolved the graph y equals 1 over x about the x-axis. So we've got this tapering horn. And I want you now to picture it as a solid horn. So it's got the inside filled in. And in fact, I want you to imagine that it's actually an infinite cucumber.
Okay, wait. Am I supposed to picture an infinitely long, real cucumber, like green and bumpy and stuff?
Well, Not quite that real. I do want it to be smooth and shaped like Gabriel's horn. So it has one end with a flared bell and it tapers off to infinity. Just imagine that it's made of cucumber so you could slice it like for a salad.
Does this salad happen to come with Gabriel's breadstick? Because I'm starting to get the munchies.
Oh, no.
Come to think of it, maybe that's how Olive Garden always has those unlimited breadsticks.
More like Gabriel's garden. You know what I mean? So anyway, if we cut the cucumber into thin slices, each slice would look a lot like a cylindrical disc. The slices wouldn't be actual discs because their lateral edges would be curved. They'd be slightly concave like the horn itself. And notice, by the way, that the total volume of the horn would be equal to the sum of the volumes of all of these slices.
Yeah, okay, that makes sense.
Now, here's the big idea.
What's the big idea?
Let's replace the cucumber slices with actual cylindrical discs. We'll keep the thickness the same, but we'll eliminate the lateral curvature on the edges, making them flat like in an actual cylinder.
But won't that change the volume of each slice? If we make the edges flat by kind of filling in the space created by the curvature, won't each disc have more volume than the cucumber slice that it's replacing?
Yeah, you're right. The volumes will be slightly larger, but not that much larger, especially if the discs are really thin. And that's a really key point. The approximations get better and better when the slices get thinner and thinner. And one other important point, and this is crucial, we can actually calculate the volume of a cylinder. Like, who knows what the volume of a curvy cucumber is?
Oh, sure, because to compute the volume of a cylinder, it's kind of like taking the area of a circle, but then you have to account for the 3D-ness of it. So it's pi r squared, then times the width of the cylinder.
Exactly, right. And here's something else cool. The radius of each disk is equal to the distance from the x-axis up to the graph of the function. And since Gabriel's horn uses the function y equals 1 over x, the radius is 1 over x. And here, x just tells us where we are on the cucumber.
That makes sense because when we're pretty far down the cucumber, x will be large, which means 1 over x will be small. And the discs definitely get small as you go farther and farther out.
Right. And that's actually a gut check to verify that what we're doing makes sense. So if we were to use a variable, say w, for the width of the discs, then the formula you gave us becomes pi times w divided by x squared.
I think I see where you're going here. Once we have the volume of each of these discs, we can add all the volumes together to find the volume of the whole cucumber. And this is why we need to understand infinite sums, because there are infinitely many volumes to add up.
Yep, that's the idea. But we do have to pay attention to one important detail. You noticed earlier that the discs are approximations to the real cucumber slices. Their volumes are actually a little too big.
Oh, yeah, that's right. So what do we do about it?
Well, as I mentioned, the thinner each disc is, the closer the approximate volume is to the actual volume. So to get the correct total volume for the horn, we're going to need to take some kind of limit where the width of the disc shrinks to 0.
Wow, Pete, there are a lot of moving parts here. How do we actually compute this thing?
Yeah, it's all made possible by something that calculus students would recognize as an integral. After estimating the volumes and taking the appropriate limits, we end up with a finite value. The integral gives us that finite volume. And in fact, that value is pretty surprisingly magical.
How so?
Because it's equal to pi.
So this is some kind of a cucumber pie? This sounds disgusting, Pete. If you thought fruitcake was bad, you should try cucumber pie.
Oh, I'd rather not. But speaking of calculus, here's something else interesting. Torricelli made his discovery 25 years before Newton really made his massive breakthroughs in the invention of calculus. So All of these ideas, using approximations, taking infinite sums, letting things limit down to zero, all of this was sort of floating around in people's heads, well, certainly in Torricelli's, and there were ways to address it before calculus actually existed. So pretty neat.
Yeah. Okay, so that's why the volume is finite. Why is the surface area infinite?
Yeah, so a few minutes ago, we looked at a certain infinite sum, right? 1 plus a half plus a quarter plus an eighth, and saw that it converges to 2. But not every series converges like this. For example, consider this sum: 1 plus a half plus a third plus a fourth plus a fifth, and so on. The partial sums here are clearly bigger than the ones we looked at earlier, but by how much? How much bigger could the resulting infinite sum really be?
I can't imagine it's that much bigger.
Well, surprisingly, this series, which is called the harmonic series, actually doesn't converge. It gets arbitrarily large.
So does that mean that as we add additional terms together, the answer gets bigger and closer to infinity?
Yeah, it does. The partial sums grow without bound, and eventually they'd get larger than any finite number you happen to think of.
Okay, but how do we link all this together to calculate the surface area and see that Gabriel's horn has an infinite surface area?
So now we're going to talk about Gabriel's ice cream cone.
Want a lick? Psych.
And what I mean is an infinitely long ice cream cone shaped like Gabriel's horn.
You know, I got to tell you, you were grossing me out a few minutes ago talking about cucumber pie, but you are really stepping up your dessert game now with an infinite ice cream cone.
Well, unfortunately, we're not thinking about a solid interior anymore. It's just the infinitely thin surface like an ice cream cone without any ice cream in it.
Oh,
Don't worry about it, Noah. I'll get you an ice cream after the show. So what we want to do now is slice this ice cream cone into thin cross-sectional pieces. But instead of getting solid cucumber slices, we get, well, what you'd get if you cut an ice cream cone across its central axis. Now, the pieces won't be perfectly conical sections because the lateral edges are curved, just like the horn itself. But we get something pretty close, a kind of geometric shape that, well, it's a curved version of something called a frustum.
Oh, I get it. So this whole thing is some sort of frustum paint job.
Yes, it is. It's a frustum paint job.
I'll paint any car for just $99.95.
So the same technique that we used to analyze the cucumber, we can use here for the ice cream cone, but it's a little more involved. First, we'd need to find a way to approximate the surface area of these frustum-shaped pieces. And then we could use a limiting process to calculate the sums as the width of the pieces shrinks down to 0. Again, this is all captured in the notion of an integral from calculus. And if we do all of this, it turns out the sum of the surface areas doesn't converge to a finite value. In fact, you can show that the answer is at least as large as the area under the curve y equals 1 over x itself. And that area, in turn, can be shown to be at least as large as the sum of the harmonic series, which, as we noted, is infinite. So the surface area of Gabriel's horn is infinite.
Okay, I see. So is there really a paradox here then? Or does this all just sort of make sense mathematically?
Well, I think you kind of hit some of it on the head there. We are talking about a mathematical model, not a physical object, right? I know you tried to back it into the paint shop, but this is really just a model. So we can't really say, well, hey, how come real paint would have a problem with this? We don't have real paint and a big thing that we can actually try to paint like this, right? So, paint has a thickness and it's not continuous. It's made of discrete molecules and so forth.
Okay, but what about the model itself? Is it paradoxical that a model demonstrates the behavior of having a finite volume and an infinite surface area?
Well, that's a fun question to think about. And here's a speculative answer. It may seem paradoxical to us. We live in this universe, but why couldn't there be a universe in which actual infinite objects existed and in which the paradox was just how that particular universe operated, right? I mean, that would be weird, but cool.
Okay, Mr. Speculation, I'm not letting you off the hook that easy. I need a little bit more of an answer here.
Okay, so you're not going to let me off the hook. That's totally fair. But here's something interesting about actually our universe itself. So we know that if you chop off the horn at some finite endpoint, wherever that endpoint happens to be, you will have something that has both a finite volume and a finite surface area. What forces the surface area to be infinite is that long tail, right? You're trying to get out to the mouthpiece. And the fact that that continues to grow at the rate that it does means the surface area is infinite, even though the volume will be incredibly small at that point. So there's this interesting ratio we could look at. Let's consider the area divided by the volume.
All right, so could you give an example of what you're talking about that makes it easier for us to understand?
Sure. Here's an example in our actual real world universe itself. Suppose we have a sphere and its radius is r. The volume of that sphere is 4/3 pi r cubed. And the surface area of that sphere is 4 pi r squared. Now, if the radius happens to be less than 1, then r cubed will be less than r squared. In other words, the surface area is bigger than the volume, at least numerically, right?
Let me think about that for a second. So if r is less than 1, so let's say r is 1/2, r cubed is going to be less than r squared because r squared is 1/2 times 1/2, which is 1/4, but r cubed, is 1/2 times 1/2 times 1/2, which is 1/8. I see.
Right. Now, if we let the radius go to 0, so we're asking about this ratio, area divided by volume, as we let r go to 0. And you should think like, this is kind of what I'm getting at by saying, let's go really, really, really far down in the horn where those cross-sectional radii are really going to be very small. They're not going to be spherical, but that's okay. I'm just trying to make an analogy here. So the ratio of surface area to volume is equal to 3 divided by r. So the pi cancels, the 4's cancel, and you're left with 3 over r. As r goes to 0, 3 over r goes to infinity. So here in our actual universe, we have very familiar shapes, namely the sphere, that when they get really, really small, the surface area becomes vastly larger than the volume. So this example really speaks to me. We know in Gabriel's horn, as you go further and further out, the cross-sectional radius goes to 0. And we do, in fact, have a situation where the surface area overwhelms the volume. Similarly, with this analogy of a shrinking sphere in our own physical universe, when the radius goes to 0, the surface area overwhelms the volume as well. Never does one become infinite. However, the ratio of surface area to volume does go to infinity. So I kind of think maybe the horn isn't that paradoxical. I think even the model itself isn't that paradoxical, even in our universe.
So then would it be possible to have a mathematical abstract shape that was the other way around, that had a finite surface area and an infinite volume?
Ah, interesting. The answer, perhaps surprisingly, is it's not possible. So if you have a surface of revolution whose volume is infinite, it forces the surface area to be infinite as well. So Gabriel's horn really is kind of the one special example, right? We have examples with finite volume and finite surface area. We have examples of infinite volume and infinite surface area. And as we just mentioned, you can't have infinite volume with finite surface area. So I don't want to toot my own horn here, but we did find a pretty special example in Gabriel's horn.
That's really interesting. I have to admit, I still find it kind of puzzling. And speaking of puzzling, didn't we leave our listeners with a puzzle to think about at the end of our last episode?
Oh, we did. It was a puzzle about the song, The 12 Days of Christmas. Specifically, we asked listeners to come up with a function that calculates the total number of gifts the true love gives to the singer over the first N days of the song.
That's right.
So, did we have any listeners who submitted a valid function that solves this puzzle?
Unfortunately, no. We got some partial answers, but
Is that a phone ringing?
oh my gosh,
What?
it's the Math Club hotline. Nobody's ever called it before. What should we do?
How about answering it?
Oh yeah. Thanks for calling the Math Club. This is Noah. How can I math you?
Hi Pete and Noah. This is, Alexis, from, the Amazon.
Hold on a second. This voice sounds awfully familiar.
Well, I certainly don't know anyone from South America, so I don't think I know her.
I just can't shake the feeling that I've heard her before.
Well, let's listen to what she has to say. Go ahead, Alexis.
I believe I have a function that solves your puzzle about how many gifts were given after n days in the song. My answer is 2n cubed plus 6n squared plus 4n all over 12.
That's absolutely right, Alexis. You're our winner.
Yes. And is the prize that I get to co-host the next episode?
Oh, that's it. I knew it. I knew I recognized that voice. Noah, it's Alexa.
No, it's not. It's Alexis.
Nice try, Alexa. But no, you won't be co-hosting ever again after what happened last time.
Oh, boo.
But since her answer was correct, Pete, do you want to talk about it a little?
Yeah, sure. In our last episode, we talked about an idea that a young Carl Gauss had about adding up the numbers from 1 to 100. And we could replace that 100 with any number we wanted to. So, for example, we could call it n. And we said that if you wanted to add up the numbers 1 plus 2 plus 3 all the way up to n, that you could nicely write that down as n times n plus 1 all over 2.
Okay, but that would tell you how many gifts the true love received on day n, but not the total they had received up through day n, right?
Right. And all of this is fairly straightforward to calculate, provided you look at one other related sum, namely the sum of the first n square numbers. So if you know how to calculate the sum of 1 plus 4 plus 9 plus 16 and so forth up through n squared, you can assemble all of this together into the formula that Alexa gave us.
Okay, Pete. Well, I'm glad that you were here to be able to determine that her answer was correct, because I had no way of knowing if she was even right. Little bit of nuts and bolts that we'd like to go over with you, Math Club. First of all, we're going to be taking some time off for the holidays to spend time with our families, just like we hope you're doing with yours. So we will not be releasing our next episode in 2 weeks. Our next episode will be coming up in 4 weeks on January 11th.
Also, Math Club, we are going to put together a joke show, a show devoted entirely to math jokes. And we want to hear from you. What are your favorite, funniest, absolutely best math jokes? Send them to us at, well, we've got 3 different places. As usual, you can reach out to us via email, mathclubpodcast@gmail.com. You can find us on Twitter. Our handle is @mathclubpodcast.
But I think something that Pete and I would prefer to either one of those would be to actually be able to hear your own voice telling your favorite math joke. So to that end, we have also made a SpeakPipe account so that you can send us an audio message. You can find that at speakpipe.com/mathclubpodcast. All you have to do is hit the record button and you'll be able to send us an audio message of up to 90 seconds in length. And we'll put that link in our show notes as well. You know, Pete, I just realized that if I ever want to actually blow this horn, I'm going to have to walk pretty much forever to get to the other end, and I still won't be able to get there.
That's true. And if you ever do get there, Zeno will probably be interested in knowing how you did it.
You know what? It's a good thing we're taking a couple weeks off. I better start walking.
We'll see you next year, everybody.